All right, you can see my screen now, I hope. So if we are all set, let's get started. Uh, okay, let me organize myself. All right, so what did we do last lecture? Last lecture, we looked at letters, a language with let bindings. So we looked at a language which had let bindings like this. Uh, we had some arithmetic, Boolean conditions, if then else statements, and so on. So this is an example of a program where I'm trying to use most of the features I introduced, something like that. So this is an example of a program that says let x be 10 in if x is greater than equal to 10, then this what? Let y equals 30 in y plus x, else the else branch says x minus 5. As an example. So such a program, when you execute, should yield the value 40. Is that good? All right. So hopefully this all squares away with your understanding so far. Last lecture, we also looked intensively at scope. What does it mean for something to be in scope? So we looked at, for example, what is the scope of X in this program? And we saw that the scope of X is this entire expression that I have just placed in the red box. Let's call this expression E sub 1. So that expression is the scope of X, which means that uh, X comes into scope when I start evaluating E sub 1, and it goes out of scope when I stop evaluating E sub 1. So we saw that. Okay. Then what is the scope of Y then? So the scope of Y in this example would be, so this is Y. The scope of Y is this white boxed sub-expression. That's going to be the scope of Y. We saw that. We also saw how to map every usage to where it's being defined and what's in scope. We saw all of that last time. Okay. We also saw this concept called shadowing last time, which I will go into a little bit more detail this time after showing you how to implement an interpreter for letters. We also wrote down some rules. Some semantic rules. We already looked at rules for plus and all of arithmetic in a very previous lecture. Very previous, I mean, like 2 weeks ago, we started looking at that. We looked at Booleans, especially we looked at and, or, all of that last time. Hopefully you saw the semantics for if then else in your recitation. Or it's there in the notebook as well, so which you're supposed to read. So hopefully you've seen some of the semantics in your notebook, if not your recitation. Last but not least, today, I would like to cover the semantics for let bindings. So this is today. Today, I will talk about the semantics for let binding. And today, I'm going to talk about scopes and how do we get scopes correct. I will also, before that, talk about the implementation in our interpreter. Okay, so I'll talk about implementation of the entire semantics, the entire evaluation in our interpreter. All right, so that's on the agenda for today. All right, so first things first, let's write down the rule for if then else as a warm-up. So in our grammar, remember we had expression was a bunch of things which we've already seen. It was a constant, expression could be an identifier. So we saw all of this. All of these cases. We saw the case for plus, we saw semantics for greater than equal to, we saw semantics for and last time with all the short circuiting, we saw the semantics for or with the short circuiting. Today, let me warm you up by starting off with if then else so that we can get our brains aligned and thinking along similar directions. So if then else, remember, has three sub-expressions as arguments: expression, expression, and expression. And the intended meaning here is this must be our condition that we evaluate. This would be the then branch. and this would be the else branch expression. So this looks like if condition, then uh, then branch expression, else branch expression. In our language, we don't have if then without the else just yet. We can have that, and in fact, I will make it kind of an easy assignment to have if then without the else. To have that in our language, we have to define the unit type. We have to define the unit type and the unit value. So we have to have a value that's basically the equivalent of Scala's unit or C++ void. And we don't have that in Lattice yet. So once we have that, we can have an if then without the else part, because that would be simply else unit. And it's a very instructive, but rather simple assignment. So let me write the semantic rule for if then else. So let's write down semantic rule for if then else. And the goal of this semantic rule, continuing from the last lecture, is to eval if then else of three parts. Let me call this econd, then, and else as the three parts. I am just giving it slightly more descriptive names so that you understand what's going on. Under an environment, I'll call env. And the goal is to create a rule like this. The goal is to create a rule like this. And the question is, how should such a rule be created? And let me look at the good cases. So let me start by looking at the good cases, and then I will go look at the bad cases, like the cases where you have to have error and handle error and all that. All right. With that being said, let me look at the first case. So the first case is I'm going to eval the condition. Under which environment should I eval the condition? I should eval it under the same environment under which I'm evaluating the entire if then else. So the entire if then else gets evaluated under the environment env. The same environment is the environment I'm going to use for the conditional part of the expression. And let's say this condition yields the value true. So let me write this rule like this. It's going to be a strange way of writing this rule. But let me write this rule in this strange way. And then let me write a rule in a different way so you can see how different rules can express exactly the same thing. Okay, so here I'm saying evaluating a condition under an environment yields true. And furthermore, evaluating then, the then part under the same environment env yields a value v. And let's call this v then. Then I say evaluating if then else under this environment should also be v then. Is this rule okay? Does it make sense to you? So this rule says if, so read this rule as if I evaluate the condition in my conditional expression and that condition returns true, then, and by the way, I evaluate the then part and I get a value v then the evaluation of the entire if then else is just v then. Okay, so this is one way of expressing the semantics just for the true case. Okay, and likewise, we would write down something similar for the false case. So what would you write for the false case? Just as a simple exercise, let me write it down. If then else, again, you have econd, then, else. Okay, and now you say, if I eval the condition under the environment, I get false. Then what should I say? I should say that evaluating the entire if then else must be the same as just evaluating the else. Let me write it in a different style, but it amounts to the same thing. I can simply say this is the same as eval else under the environment. This is a very compressed way of writing exactly the same thing. I could have said on the top eval else under the environment equals V else. And instead of saying this, I could have said V else. This is just like refactoring or giving things a name. If I don't need to give things a name, sometimes I can say things directly. I can simply say evaluating the if then else when the condition is false is the same as evaluating the else. Is this okay? These rules should be very easy now. You have seen plenty of these rules, and I hope everyone's with me. All right. And last but not least, we have to write an error rule. What is the error rule going to be? Can someone help me with the error rule? What's the antecedent for the error rule? We have the same setup. You're trying to eval if then else. While I write down, think about how do you when do you get error here? E cond, E then, E else. So these are the three arguments under an environment E and V. And then under what condition should I flag error? Not a Boolean type. Very good. What is not a Boolean type? So could you be a little bit more specific? Excellent. So eval E cond under the environment E and V is not an element of Booleans. If that is the case, then this whole thing is just error. Excellent. Very good. Is everyone okay? So these three rules will do it. For example, can you tell me what happens if I have an expression like this? If 10 greater than equal to 20, then something else, let's say 0 divided by 0. So what should this return? In what would you expect this expression to return? Error, right? Error. Now, if you understood, exception or error, right? I'm going to pretend initially be very strict about my semantics and return error. But as you will see, that makes my life really, really difficult. So I'm going to go back to a case where I'm just going to throw an exception whenever I hit error and not bother propagating error carefully. Okay, so I'm going to do that, but that will come in a second. So right now, this should be an error. But which case is it that we match to when you get an expression like this? Which of these cases is helping you decide that it is an error? So let's call this ITE true. Let's call this ITE false. So I give names rules for a reason, so I can talk about them. And let's call this ITE error. So which of these three rules do you think makes us conclude this? ITE false. Very good. So you see what is happening is when you hit the else branch and let's say for some reason you got an error, the same error gets returned here, right? So you see you don't need extra cases where you may have needed it in other sub expressions, like in plus you would have needed a case where the first expression returns an error. You'd have needed a case where the second expression returns an error. But this way of writing is very succinct in a sense that you don't need to write those cases because they're already there in your code or in your semantic rules. Very good. Okay, so let's now get down to business. The real business we are here for is to write down the rule for lead bindings. So I would like to write down the rule for lead bindings. So this is the main thing. Okay, if we had trumpets and fanfare, you can imagine those trumpets, okay, blaring in the background. So that's, now here it comes. So what's the rule for lead bindings? So my goal is to take a lead binding and evaluate it. So I'm interested in evaluating an expression of the form let identifier, let's call that ID, expression E1, expression E2 as arguments, and I'm doing this under environment ENV. And I want to know, how do I evaluate this? Okay, so before I go there, there is a question. Which one was the better syntax, ITE true or ITE false? So let's going back to this. I don't think there is a better or worse syntax for these rules. Uh, Whichever one you think conveys the intent clearly is going to be better. The reason I'm walking you through all of these is sometimes I would write things this way. I would write things out this way with V else and V then on the top, because there is something else I want to say about V then or V else. So then I would write it up as an antecedent and give it a name. Often enough, if there are no conditions on V then or V else, I would just write it at the bottom as an eval. Okay, it's just a choice I have made, because the goal of these semantic rules is for me to convey ideas to you, and for you to look at those ideas and say this makes sense and that doesn't make sense. So it's basically conveying my design choices before I go ahead and write code. So it's just notation. That's all it is. And if it doesn't convey the ideas clearly, it's bad notation. So there is no right or wrong there. Right? You just do the best you can, and hopefully you convey the idea clearly, unambiguously. All right. Okay, good question, John. All right, so let me get to the let binding now. All right. Okay, so now I am interested in doing this. What is this? This is just abstract syntax for let ID equals E1 in E2. This is what it is. All right. Now, what is E1? ID is the name of the identifier. This is a string. This is a string. E1 is basically the expression you are going to declare ID and assign it to. And E2 is the body, the after the in, it's the body. So I want to do this. So let me write down the rule and actually explain what the rule means. So what is the first thing? So if I am supposed to evaluate this entire if then let binding, what is the first thing I should evaluate in this let binding? Let me ask you, what is the first thing? So if I have let ID equals E1 and E2, and I'm supposed to evaluate the whole thing, what should I evaluate first? So let me write down a series of steps. And then let's try and write these series of steps in a semantic rule. So you see the mapping between semantic rules and some series of steps. E1, excellent. So eval E1, under what environment should I eval E1? Under environment env. And this makes a big difference, as you will see in a second. Okay, I'm going to say, let's eval E1 under environment env. And let's say this is successful and it returns a value V1. Okay, so suppose this is successful. What's the second thing I should do here? So I have evaluated E1 and I have successfully gotten it to be V1. Okay, now what? Now I should implement the mapping from ID to E1. So let me say implement. How do I do that? Mapping or binding from ID to V1. Aha. So yes, ID equals V1. Laura, you're right. But the question is, how do you do it? Okay, very good. So John asked, would E2 operate in ENV plus ID? Excellent. And you should just look below. Jacob's got it exactly right. What you simply have to do is you have to extend your environment. Okay, so you have to extend your environment. So extend the environment by mapping ID to V1. And this you write in this strange notation. So you write it in this math notation that says ENV circle ID maps to V1. So remember, ENV is a function. So Jacob got the Scala notation right. I'm just giving you the math notation. This is the function. And you're saying take this function and extend this function by mapping ID to V1. So what does this mean? So this means that there are two cases. ID is not in the domain of environment. If ID is not in the domain of environment, then this new environment, let's call this new env. So then new env will now have id, and new env of id will be v1. Okay, if id were already in the domain of environment, what should I do? So if the ID, the identifier I'm encountering is a fresh identifier, I haven't seen it before, then I add the binding from ID to V1. If ID were already there in the old environment, what should I do? Hint, it's a trick question. Replace it. Very good. Replace it in the sense, do exactly the same thing, forget about the old binding, and say new environment of ID is V1. So what am I going to do is I'm going to just replace ID by V1. If it didn't exist before, it exists now. If it existed before, it's forgotten and replaced by whatever is now. Is that okay? But for everything other than ID, you still retain whatever the old environment said it was. So if you had Y and Z and things that are not ID, you retain what the old environment says that it should be. And that's exactly what you get with what Jacob suggested. Is that okay? Okay. If this is all clear, let's implement it in our semantic rule. So let's do it. First step, eval E1 under the environment, and let's say that's V1. Furthermore, V1 is not an error. If V1 is an error, we have to bail. So we say V1 is not an error to continue. And then we say what? So there are two ways of saying the rest. Let me say it the succinct way, and also say it in the way that you're used to, which is slightly more verbose. So in the succinct way, you simply say the result of the entire let binding is simply the result of E2 under environment extended by mapping ID to V1. That's it. So this is all there is to it. Okay, so this is all there is to it, in the sense that you're really just, let me erase some of the stuff from below. You're really saying that evaluating a let binding under an environment ENV is the same as evaluating E1 under that environment, obtaining a value V1, making sure V1 is not error, and this is in the antecedent. If all of this is true, then evaluating the let binding is the same as evaluating the E2 part of the let binding after the in under the environment ENV with ID mapped to V1, where V1 is the result of evaluating the declaration, the right-hand side of the declaration. Is that okay? It's as simple as this. All right. Now, of course, you could have written this out in a little bit. So let me write it out in white. So I could have said V2 equals eval E2 under ENV map to ID arrow V1, all of that. And then I could have simply, instead of this, I could have simply said V2. But whichever, they are both the same. Both the semantic rules express exactly the same thing. I could have called it V2 and put it out in the antecedent, given it a name, and then called it V2 in the bottom of the line. Or I could have simply said eval, because there are no conditions about V2. There is nothing that I need V2 to satisfy. The entire let binding is just E2. It's going to eval to E2. Okay, good so far. Now, are we essentially saying that ID doesn't exist in the scope of E2, or are we mapping the scope of E1 there? No. Okay, I'm really glad you asked this question. So we need to clear this confusion, right? So what is happening here? So let's look at this rule carefully. So what this is saying is E2 is evaluated in an environment that has ID declared. So in fact, this is exactly where I'm getting ID is in scope. Now let's talk about being in scope, right? So Sahil raised an excellent point, right? What does it mean to be in scope? Let's now talk about being in scope. Being in scope means that something, so let us say ID is in scope. That means that in the current environment, there is an binding for ID in the current environment. That is exactly what being in scope now means. So is ID in scope for E2? It is in scope for E2 because the environment for E2, this environment, or let me show it here, this environment here has ID in scope because it's the old environment extended by mapping ID to V1. So we are just extending the environment, but that's super important. So don't underestimate the environment. The environment is actually playing a huge role. And in fact, I'm going to spend uh, about the rest of the 45 minutes, Sahil, to kind of drive home this point. Exactly your point. I'm going to talk about how did we solve the scoping problem. We just did, but it's not at all clear that we did. So I'm going to talk about how we solve the scoping problem. All right. So I'm going to spend about 45 minutes answering Sahil. Okay, let us talk about this, right? So John, excellent question. Hold on to it. We'll talk about shadowing, right? How is this solving everything? It doesn't look like it is, but it is. So let me just complete my thought and let's go to some code. Let's talk about implementation. And then let me talk about how is this actually working? Why does this work, right? We need to see that. So let me talk about that with some example. So let me talk to you about then let me write down this rule nicely. So the rule says eval let identifier E1, E2 under env environment. So you say if I eval E1 under the environment and I get the value V1 and V1 is not error, then the whole thing is just eval of E2 under, let me just give a name here so that it doesn't get too cluttered. Let me call new environment. Let new environment be environment extended by mapping ID to V1. Let's write up in the argument, in the antecedent. Then I say it's eval under the new environment. So this is exactly the same thing. I've just written it out a little bit better. Okay, I've just written it out a little bit better. Hopefully you can see that. So I've just called this new environment. Instead of writing this right-hand side down, I've just called it new environment. So you see it's a different environment, which is extending the old environment by mapping ID to V1, V1 being the result of E1. Now there is an error rule which says if eval E1 under the environment is an error, then eval the let binding of ID, E1, E2 under the environment is error. And this is important. In my environment, I make sure that all these mappings that I produce, never map an identifier to error. So there is no error in my environment. Okay, so garbage doesn't leak into my environment. Garbage stays mainly in the interpreter, doesn't leak into the environment. This is an example of a language design I make. Is that okay? So as an example, I'm making sure that none of my rules will ever put an error value in the environment. Is that important? No, but I'm just showing you like these are some kind of guarantees that I can provide in my language design or my interpreter design. And this leads to something called a meta theorem or a meta theory. Again, I promise no meta theory for this class, so I leave it at that. But it is important. You know, in a graduate class, you would prove these kinds of facts. You would prove them through induction that no, the environment through all the eval will never bind any identifier to an error. It will always bind an identifier to a non-error value. So stuff like that is important, and you have to guarantee that. Okay, if this is all clear, let's take a second to then go ahead and see how do we implement all of this, all right, with a focus on how do we implement let bindings. Then I'm going to talk about how did we get scoping correct? Did we get scoping correct? If so, how did that happen? All right. And by the way, as an example of getting scoping wrong, look at your project one. it's actually an extra credit problem for you to get scoping correct there. Uh, you would see that in project one, and this is kind of the secret, extra credit secret, that we got scoping wrong there. I did not implement scoping, and you will realize that with some examples. And I'm happy to discuss this offline, right? How do you do it correctly for project one? But right now, let me show you that this implements scoping the way we expect it to. So let me go ahead and show you implementation then.